Hi everyone, thank you so much for joining us today for our guest speaker session. We have with us Nataniel Ruiz. Nataniel is a senior research scientist at Google. He completed his PhD at Boston University, advised by Professor Stan Skarov. He is mostly known for his work in personalization of image and video generation model, including his work Dream Booth. Thank you so much for your time, and I'll hand it over to you.
Yeah, hi everyone. Thank you so much for inviting me. Let me share my screen. Today I'm going to be presenting some interesting work that we did last year. Um, actually, yeah, today I'm going to be talking about two cool works that we worked on last year. These are student works by our two interns that spent the summer and a little bit of fall with us. I think the kind of how to merge these two ideas going forward is a little bit in the topic of virtual generative worlds. And today I'm going to talk about two works. One is generative camera controls with ReCapture, and another one is Unbounded for basically like character simulation and unbounded video games generation. So yeah, just a quick intro on me. Yeah, my name is Nataniel, and I'm working at Google for a bit now, for a year and a half, and we've been doing a lot of different work in personalization of image and video models. Mostly image, but now transitioning a bit to video and LLMs. Yeah, these are some of the works that we've done, like Dream Booth. I was lead author there, and then other works like Hyper Dream Booth, etc. A lot of these were with amazing students, and we're continuing that trend looking at the future. So let me start with the first work, which is Unbounded, and then I'll go with the ReCapture work, which is generating new camera motions for existing videos, and then try a little bit to tie them together. But yeah, so let's start with Unbounded, which was work done by Jialu Li as lead author, so our student. And let's start by talking a little bit about this idea of generative infinite games. So what are generative infinite games? So generative infinite games are, as basically we came up a little bit with this concept for this paper. So generative infinite games are essentially video games where the game mechanics and graphics are fully subsumed by generative models. So that's kind of the generative part of the generative infinite game. So yeah, all the game mechanics, environments, character states, character actions, and graphics are encapsulated within generative models. And I'm going to show a little bit of related work in a second that shows that, a lot of people have been kind of thinking of this, of how you can have all of the game engine and also maybe even the graphics engine inside of a generative model. But we have this spin on this idea, which is the infinite part, where basically we came to this idea saying that there exists like games like roguelikes, for example, where you can have like a incredibly high amount of variability, right? And other types of games that try to like basically become infinite, but a lot of these are not narrative driven because it's really hard to create a narrative driven game that is unbounded in some sense. And one of the things that we notice is that with generative models, with LLMs, that can kind of like start to confabulate and create new stories when you're working with them. We thought, yeah, this is kind of a window into allowing for an infinite game that is narrative driven. So an infinite game, as defined by James Carse, is a game played for the purpose of continuing the play with no fixed boundaries and evolving rules, and LLMs can allow for this. And one big inspiration for this is basically like pen and paper role-playing games, for example, Dungeons and Dragons, which are narrative, right? You're creating a narrative with people playing together, and there's like a game master that leads the play, and then everything happens within the boundaries of the rules that the game master sets. But the game master also has like some meta rules that they can kind of start creating, and in the end, what happens is like an expansive storytelling game that is virtually like unbounded. You can do whatever you want, and then the game master will tell you what happens when you're trying to do whatever you want. And this is an experience that is basically impossible in video games. And maybe like the closest yet, some of this has gotten to be like infinite is what I was talking about, like roguelikes and stuff, but a lot of that is like expansive game mechanics, right? Like, oh, maybe game mechanics interact in different ways, but maybe the narrative part is not really there, right? Because it's really hard to create narrative. But now that we have LLMs that can create a lot of text that and reason in some sort of ways and create text that really makes sense in a lot of situations, then this can power this narrative aspect for these games. So yeah, combining this idea of generative with the idea of infinite, I think is possible now, and it's going to be really exciting in the future to see how you can have a fully fledged game engine that creates narrative, also creates maybe even game mechanics, and also creates like the graphics of the game at the same time. And that's the dream that we started with this project. So yeah, this is the what we came up with, Unbounded, a generative infinite game of character life simulation, and thanks to all of the co-authors. And the core premise of this is that you have a character. Basically, this is very inspired with like kind of like Tamagotchi type games where you take care of a pet or something. You have a character that has different needs, for example, like hunger, sleep, etc. And you have to like take care of the character, but also you can interact with the character and you can create stories with the character. And you can take the character to new environments and do different things in new environments. And the idea is that all of these things are encapsulated within the like nothing is happening outside of generative models. So everything is happening inside of the generative models, such as the game mechanics. So if you feed your character, the food bar is updated inside of a LLM. So the LLM is keeping track of the game mechanics and the rules of what happens, right, when you do certain things. Also, the narrative is being kept track by the LLM, and the LLM is creating a narrative with based on your responses. And the other thing that happens is we have a generative image model that is generating the frame, so it's generating the graphics as well. So we have everything encapsulated, graphics, mechanics, and narrative inside of generative models. And that's like the innovative idea about this work. So here you can see Archibald the wizard, and he has like hunger and energy bars, etc. And you can see how basically you have a story created by the game engine, the LLM game engine, and you can see that Archibald is getting hungry, and I tell Archibald to go to the flowery meadows and forage for pears, goes to the flowery meadows and eats the plate of pears, and you can see the food bar updating there. So the LLM is taking that into account, like that we told the wizard to go and eat the pears. Wizard has eaten the pears, and then we have an updated status for that. And then we can basically keep the narrative going and construct our own narrative. So telling our archivist to go head back to the classroom and study arcane magic, and the model can kind of give a good feedback on that and start to create the story. We'll also talk about another cool thing that we did here, which was very important, is to try to put the character in different environments. Yeah, so quick recap on like the work leading up to this, on very focused on people that were working on generative vision models mostly, and crossed over into the kind of game generation world. There's also other types of work of people that are specialized in procedural game generation, etc. That are crossing over into the AI space more, or have been crossing over for a long time. But this is this paper is called Game Engine. It's from Google, Avalowski et al. 2024. And the idea here is that you can basically learn the Doom game engine by just with a vision model, a generative vision model, by feeding it a ton of trajectories of Doom gameplay, and then generating this as fast as possible, right? And then they achieve good frames per second and good consistency for this world with this work. So this kind of show that you can, given an existing game, you can maybe try to absorb it and learn it with a model, and then generate new, maybe areas even of the game, like let the model hallucinate new things, right? Genie is also a Google work that is really great. Basically learns a text to game model or image to game, for example, in this case. So for this case, like you feed it these images and it's able to come up with a game that you can actually play using WASD keys. And so you learn on top of like a lot of 2D platformers, basically a video model in some sense that has inputs, action inputs, and then you're able to predict next frames. And then this work has been getting much more advanced and now supports like a wider variety of games with much higher fidelity. But it's still in the same vein as you kind of create a full game using text and then you can kind of play within it. But a lot of the mechanics are probably very similar to the games that you've learned on, right? Which kind of makes sense. So this kind of leads us to Unbounded. It's a little bit, so it's inspired by these, but it's a bit different because of this infinite component that we were talking about and this narrative component, right? Because these other works don't really have like a narrative component to them. So yeah, the main components of Unbounded, and I'm going to talk a little bit now also about the contributions that we have, the technical contributions. So main components of Unbounded are real-time controllable text image generation model capable of maintaining character consistency and environment consistency throughout the generative game. So this real-time part is pretty important because you want a model that generates images quickly, and that's also why the images are, probably if we did it this year, the images would be like, the graphics would be a bit better, right? So we had to use an open source real-time model. And then maintaining character consistency and environment consistency is actually pretty hard. So one of our main technical contributions is in that domain. And then also a large language model that acts as a game engine for interactive user experience. And we did a lot of work to make this large language model fast as well because of the delay that you need. So actually to get interactive speeds, you need a refresh every 2 refreshes, 3 refreshes every second. And we got to that speed at least in our work. And you can probably further speed it up. But yeah, it's actually hard to think of. So first of all, it's hard to have a vision model that generates images very fast enough to get like several frames per second. But now you have to think of the large language model that has to generate the narrative and the game mechanics, and that model also has to be fast. So we did a lot of work there. So the final contributions are a regional IP adapter for character and environment consistency, which is related to this first point of character consistency and environment consistency. The second contribution is a distilled, small, and fast LLM game engine. And the third contribution is like a little bit more nebulous, is conceptual contributions surrounding generative games overall. And I think we talked about these like with the infinite game thing and generative games, like everything is subsumed into generative models. So here's a full user flow for Unbounded, where you have the game setup. You have user instruction input where you can tell it kind of like the vibe of the story that you want, and also the initial environments that maybe you want to generate. So you can give it ideas for the environments, or it'll generate them on its own. So in this case, you could say like, oh, I want a forest and a pond, or you could just say like, oh, I want like a forest vibe kind of world, and it'll generate some of these on itself. You also have you can also talk about the character personality a little bit. So that is information that the model will take into account in the future when generating the story. And this is one thing that we really wanted to have, is being able to give a character to the model yourself and now play as that character specifically. So you can input a character, and in this case, I'll input this young witch Anta, I think is how we call her. And the model is able to now kind of like, let you play with Anta in the game. And the topic is going to be dragon hunting. So you get game environment generations. You generate different, this is a pre-processing step where the model generates some environments like a forest, pond, village, and mountain. And then the game starts, basically. So you start the game at the first environment with the character in the first environment, and usually full bars, or some bars are at least full. And you have entering the forest. So the model starts to generate a narrative. And then between each frame there is character action. So you could basically do two things. You could either wait until the next frame, so it just keeps generating things until you intervene, or you can intervene immediately and just start to direct the narrative of the game. So the game can play itself basically in some ways, but some things can't be done by the game itself, like feeding the character and doing other things. There's a question. Let me check. Okay. Yeah, if there's a question, you can unmute yourself and. Okay. So yeah, we have different frames for this, like entering the forest, exploring, encounter the dragon. You can see how dragons generated in the scene of Antha. You can see also how the bars are updating. So the hunger is going down and energy is going down and fun is also going down. So all of the bars basically have a decay, natural decay to them, and then you have to refill them by doing certain actions. So now you get like different choices. So at that point you can intervene and say like, yeah, I want to do something. So you intervene using text. So all of this is text interface and everything happens through text, either advancing the story, talking to the character, or doing certain actions. So in this case, you could say, like, oh, hunt the dragon or go buy a potion. In this case, you say hunt the dragon, right? So this is one branch, for example. Hunt the dragon, and then you can see Anthus fighting the dragon with magic. The dragon retreats. You can see the dragon retreating there. And then Anta rests and eats. So this is a user action, rest and have food. So you can see the bars going up when we say that. So you could be as descriptive as you like, go find blueberries and eat them or something. You might see the blueberries appear in the frame, or you can be vague. And this all depends on kind of game design at that point. And this is going to be a huge field in the future, probably, of like generative game design, of how to make your generative model have the behaviors that you want in gameplay, right? And that's probably going to be pretty hard field. But it's similar to what happens now with, for example, coding. Like a lot of coding nowadays is done by using AI, right, to do coding, and a lot of kind of traditional. I'm not saying like the techniques are being replaced, but there's a new kind of world where prompting the model is very important in order to get what you want. So that's going to be very relevant, I think, for like coding in certain behaviors into your game in the future. And I'll tell you a little bit of how we did that for this game specifically here, which is probably pretty simplistic, but in the future, it's probably going to have like more like deeper techniques. So yeah, rest and eat, and then explore the pond, and you can see that the character changes environments here, and you can see that how the environment is pretty well preserved when the character goes to that environment. So there's another branch here. You can think of different branches here, like branch 2, where we go to the village and buy some magic potion. So yeah, just flee the dragon, go to the village, change environments, and get magic potions. Yeah, and you can buy the potion and then have some food, and then you can see different updates for that scenario. So this is how the game is supposed to work. If there's a question.
Yeah, so I want to ask that between these actions, for example, if the input is explore the pond, is it generating like a single frame which just shows it is at the character is at the pond, or is it like generating a few frames that is showing an action of exploring the pond?
So right now it's I guess I would say like our animation component is not super advanced in the sense that it wasn't like extremely smooth and you couldn't see like sometimes like actions taking place as well as you would want to, right? But yeah, it's generating several frames. So you have like an updating thing. Like I would say like 3 updates per second. So you have like like something. I'll show in a bit like a little bit of what we have for that. But you can think of this getting much more advanced like very soon, right? If people are exploring like distilled image models. And I think maybe one of the issues that we had for this project is that we were trying to do a lot of things at once and trying to be very ambitious on all of them. And in some sense, you have to have some compromises. So animations and real time like generation is not going to be as good when you try to explore like several fronts at the same time. But I am hoping for work in the future that does these things, and I'm really excited. But until now, I haven't really seen anything doing exactly this. So I encourage anyone, like if you want to talk to this about this to your friends that are interested um, in this area. I feel like there's so much to do, right? Like you can explore the animation front, you can explore the real-time part, you can explore the game mechanics part, like how to integrate better game mechanics into your game, like a ton of different things. So yeah, I'm hoping that this happens sooner rather than later, because I think we have the components to do it. And yeah, and also we can't work on everything, so we're working on this uh, as well, in some things. But yeah, we can't do everything at the same time. So I hope the community kind of like gathers up and tries to do it, because it's really interesting. Um, yeah. So let's keep going. So let's talk a little bit about the controllable text image generation here. And this is one of the main we kind of had an idea of what we wanted when we started the internship, and then it was all about doing it. So we wanted this like character simulator. We wanted to have unbounded interactions with the character where you could talk to the character, it would respond to you. We wanted for it to be fast. We wanted to take the character to different environments, and we wanted to have game mechanics in the game that would update when you said like go eat, and you didn't have to say +2 points to the eating bar or something, right? Like just it would update it by itself. So those are our 4 or 5 basically requirements that you want to have at the beginning of an internship. So it's kind of you hit some roadblocks, and one of the roadblocks for sure was this part of controllable text image generation, where we want to have a fast model that generates images that are good quality, but also be able to integrate a character that we want, and also be able to integrate an environment that we want, and have both of these be consistent. Yeah, so how we do this is, first of all, to do fast generation, we have an LCM model, a latent consistency model for, I think this is, yeah, SD 1.5, I feel like we were using. So that, is 2 to 3 frames per second versus 0.1 frames per second, which is very slow, right? So at least now we have something that's faster, that can give like kind of real-time updates, although the quality is less, right? So hopefully in the future we see an improvement there. So next thing is we use Dream Booth for character consistency. Just because we realized that character consistency is extremely important, because if your character is changing an appearance between frame to frame, then it really breaks the game, right? Like it makes it horrible, and you don't want to play. So it's really important to have perfect character consistency. Dream Booth is one of the best ways to achieve that, and we know that you could have a setup phase for your game, which maybe lasts 10 minutes or 5 minutes, and you could do Dream Booth in that time, right? So you just set up a game, and then you come back, and then you're able to play it. It doesn't have to be immediate, right, at the end of the day for some of these things. So that's why we elected to go with Dream Booth for character consistency. And then the last thing is this regional IP adapter. So then the question was like, okay, now we have some character, we have good character consistency, but also we want to have an environment. So we want to have this witch in this desert, right? And that's something that was actually pretty hard to do. You could do some things like magic insert. So I have another work where I can kind of like drag and drop a subject into an environment, and it works really well. The quality is really great, but it was very slow, right? And here you want to do something fast. So we wanted to do, we had to work on the model itself and on components of the model in order to get this working in just one inference pass. So here what we did is an IP adapter for environment and character consistency, and we kind of like came up with a new type of IP adapter. Yeah. So one thing that we noticed is that there was interference between environment and character conditioning. And yeah, you would get like bad results if you tried to do just kind of like IP adapter with an environment and then rely on Dream Booth for the character consistency. You kind of had to have both in the IP adapter, and then when you try to do it naively, it would also fail. So basically just saying IP adapter with multiple conditionings failed, and we had to find an improvement, and we come up with this new idea of regional IP adapter. So yeah, you can see it here, for example, just going through like this character in this environment or this character in this environment. You can see for IP adapter, you have completely fails. Environment maybe is good, but you can see two dogs here that are not the same dog as the one we want. And for this one, environment's pretty good, but you can see like, yeah, the dog is very, like, there's artifacts and there's like two dogs here as well. Not very good. Yeah, we'll check the next ones in a bit. But you'll see how we fix this. So yeah, we introduced this idea of this dynamic regional IP adapter with a block drop to mitigate interference. The idea of regional is that we apply condition to a relative region instead of the full image. And for the environment, we'll apply the condition to the pixels that correspond to, and the regions that correspond to the environment. And then for the character, we'll just apply that conditioning to the part that corresponds to the character. And we do this using masks extracted inside of the model in a very interesting way, actually. So yeah, that's this dynamic part, is the region masks are dynamically extracted from cross-attention layers during the forward pass. And I'll talk about that, yeah, I guess here is important. So you have the query and keys, and you're able to basically extract masks from the attention block. This is kind of similar to what was it called? I forget the name, but yeah, it's similar to early work on prompt to prompt. Yeah, that's the work. So there's a Google work from a couple of years ago, prompt to prompt, which was able to like extract masks from the forward pass from the attention layers during a forward pass of the network for different things, for different words. So let's say if you say like the word which, then you would able to extract rough masks in the attention blocks for that character, and they use it to let's say upsample the, like if you say the word which, then you could upsample things in the text space, for example, red, and then the which would become more red, right? In this case, this is not what we want to do. So we don't want to do editing of the generated image. What we want to do is have good character and environment consistency. So what we do instead is we extract these masks and we only apply the IP adapter conditioning on the parts that interest us for each thing. Yeah, so this is that dynamic mask part, and so you can see here, and the last part is this block drop. So we drop blocks for this process that have low quality masks. So you can see when we try to extract this component v-which in the different attention blocks for the down blocks, mid blocks, and up blocks, you can see for some of these, it's very clear actually where the which is, so there's good localization. And for some of these, there's bad localization, like the mid block. So we kind of ignore the ones where there's bad localization, and we focus on the ones where there's good localization. And we did that for one specific model, but you can kind of like derive these things for different models and then use the blocks that correspond to each model. In the end, once you put everything together, you have an IP adapter result here, which is like the baseline result. And then with block drop, you can see it's already improving, right? So you can see like the character forming here, environment's pretty good-ish. I mean, it's not that good. And then for, the character is starting to appear, but it's not really the same dog. And with the regional IP adapter that we propose, you can see the character and you can see the environment is pretty consistent. So it's actually kind of exactly what we wanted, in my opinion, because the IP adapter part extracts the environment features and then uses those features to condition the model for the future generation. And since it's in feature space, you don't get exactly the same scene and just the dog pasted in some location, which would be a bit boring. It kind of generates a new angle or interpretation of the environment that you're looking at. So this is perfect for our story-driven approach, right? So you can see here, like for example, it's like a zoom in almost of these stairs, and you can see the character here. Yeah. So some quantitative comparisons here. Yeah, so this is there's the state of the art at the time for this type of task was story diffusion, and there's also like IP adapter baselines that we can compare to. And for all metrics, for an evaluation data set of 5,000 triplets, for all metrics like clip, metric, dyno, and dreamsim metrics, we achieve much higher scores. And also for semantic alignment, we have the same score as story diffusion. So our approach outperforms previous approaches in both environment and character consistency. Yeah, so this is an ablation, and you can see so block drop improves both environment and character consistency compared with the baseline multi-IP adapter. And once we integrate everything, you can see, for example, character consistency, which was our most important thing, improves vastly here, so this is why we stay with this. And environment consistency is also is doing pretty well for some metrics, and then very similar for some others. So we pick this, obviously this row here, which we think is the best. So regional IP adapter has this character consistency and text alignment, and maintains comparable performance and environment consistency. You can see these scores are not very far from each other. And in the end, like from our qualitative tests, like we found that it was the best performing, and we stuck with that, which is really important to have very good character consistency for a game. Yes?
Does this work for multiple characters as well, or is the consistency only for single character?
Yeah, that's a great question, actually. So I think this technique, first of all, is very general. So if you can change the environment to anything else, so you could you could have like character and character 1 and character 2, right? So you could have 2 characters, and you could do an this regional IP adapter for 2 characters and an environment, right? So it extends to multiple things as well. It doesn't have to be 2 things. So I think since it wasn't like the focus of our paper, we didn't extensively evaluate that part, but we could, and I think it's very interesting for people to start using something like this in the future. But for this specifically, we were focusing on 1 character because since the game is structured in that way, we're just focusing on 1 character. Okay, so yeah, some qualitative samples. Yeah, and you can see, like, for example, story diffusion, which was a state of the art, doesn't show the which here, and you can see ours shows the which, so this is a big one, and also has better semantic alignment and environment alignment. Same thing here, so you have some environment alignment here in story diffusion, but the character is not quite there, and you can see for ours, you can see the character there, which is pretty good. Here you have character consistency, but the environment is not very good for story diffusion, and the same for ours. We have both environment and you have the character right here. Yeah, and for the paper, we had a bunch of characters. I don't know how many we showed in the paper, but yeah, it was we had like 6 to 10 characters when we were training this model, and it was pretty fun to try out new characters. Yeah, so let me talk a little bit. Actually, yeah, we're going a little bit slow, so yeah, I'll try to hurry up a little bit as we finish this. But let's talk about LLMs as game engines. Again, we want the LLM to generate everything. Basically, game mechanics, we want it to generate narrative, and yeah, we want these instructions to then generate the images using the image generation model. So what is a game engine? And the game engine would have like environment control, like what environment the character is at, and taking it to different environments is important. It would have coherent story generation and narrative, right? Where you could even talk to the character and it would respond. You would have game mechanics. So in this case, it would be the like health, hunger bar, energy bar, etc., and how to update those. So some rough game mechanics on what to do so that those update. And it has prompt rewriting was an important one because you need to rewrite a prompt so that the image model can generate something that looks good, right? So things that we write sometimes are not very good prompts for image models, and the LLM can make this work. So for this, what we did was distill Gemma 2 billion for real-time interactive responses. So again, like it's super important for us to do this, to have an LM that acts fast and can generate multiple frames per second or states per second in this case. So for that, we basically distilled a larger LLM that can do a lot of these things innately into the smaller LLM. So that's another big finding, right? Is that big LLM like a ChatGPT or Gemini, like the more advanced versions, can already generate some rough games by themselves that have some consistent mechanics and stuff. So that's already very, very interesting. And you can explore this and exploit this capability. So what we did is we had data collection of diverse types of adventures for this type of game, and you have multi-round interaction data that we've generated between world simulation LLM and a user and an LLM that is simulating a user. Yeah. So first you collect data. And then, yeah, I guess here basically I'll just show it here. So so you collect topics, you filter them, and then you can go to the kind of user simulation where what you're trying to do is you have the topic pool, you insert it into the world LLM, and then you're going to create a lot of different game histories, basically, where a user LLM is interacting with the world LLM and creating kind of like trajectories. And in some sense, this is similar to what Game Engine is doing, right? But they're doing it with the Doom game engine. Here we have like we're generating fake trajectories for the game that we want to generate, and then we're distilling a we're distilling a smaller LLM to fit into this. Now, this is an important part because we were talking about how to generate these game mechanics, right? So here we do it through prompting, right? And through the initial like topic selection, etc. So so the first things that we want to do is like have this world LLM, like which is the larger LLM, you can instruct it to have certain mechanics. So you can instruct it to have like a hunger mechanic, an energy mechanic, and then those end up in your histories of generated trajectories for the game. Now you can think of like you generate some initial trajectories, and then you do some debugging, and you go in and you see what mechanics are working, which ones are fun, and then you can rewrite your prompt. You can also think of this world LLM as you can also fine tune it with like human written interactions, so that you have the exact specific mechanics that you want, even if the larger model isn't able to do those, right? So let's say the larger model isn't able to do some specific mechanic. I don't know, like some mechanic that you invent, like music playing gives bonuses to your allies or something like that, right? And it doesn't do it consistently. So you would be able to first fine tune the larger LLM with some trajectories of this type of interaction, and then you would hope that you can generate more, and then you can distill a smaller LLM based on that. So I think this is like what probably the initial step of game design using LLMs would be. But then there's probably like a whole field to be born from this specific idea. Yeah, so let's talk about comparisons with large models. So okay, so what we did is basically we take GPT-4o to be the best type of game mechanic simulator, or like game engine, and then we evaluate based on that on our distilled versions, and we also evaluate based on like vanilla versions of the small models. So we evaluate for different things such as like state updates, environment relevance, story coherence, and instruction following, and we see that our fine-tuned models are. Can we get a mute on? Okay, thank you. So let me go back. So we can see that our fine-tuned models for these base models are achieve higher scores for all of these. And our models actually, so for the next, oh, I thought I had a next slide, but anyway, our models are actually achieve similar results even to like the upper bound, which is GPT-4o. And this is just distillation using 5,000 data like trajectories, basically. Yeah. So final summary for this is these are actual game states. So like these are games that we've played with Unbounded, and these are just the frames. Obviously, we didn't put the text here. And you can see like different things that happen, like the characters. There's good character consistency, and we have very different characters for each of the games, and characters are exploring different environments. You can see there's good environment consistency between the the frames, and you can see the bars basically kind of deplete in a monotonic way until the user does some sort of intervention like feeding the character, etc., at which point you see them increase, and you have the kind of consistency of the game mechanics simulated here for different like worlds. Yeah, and we're trying to look into open sourcing this and like releasing it to the public, and hoping that people play with it a little bit, but also look at the potential of this kind of new field of generating video games using AI in different ways. Especially these narrative-driven games, I think, are interesting. And also another key, I think, idea here is the game mechanics. So trying to have models that generate game mechanics, I think, is very interesting, instead of having them hard-coded. Yeah, thank you. Next is ReCapture, and we don't have that much time, so I probably I'll leave. Is there any question? Maybe I can take one question there if there's a question. If not, we continue. Okay. All right, so yeah, let's go into ReCapture. So this is departing a little bit from the virtual kind of like worlds, but I think it has applications into that field, because this is going to be all about re-angling existing videos. And this is from this name, like generative video camera controls, I think is very, very cool kind of concept. And the thing is, maybe you can do this even in virtual world. So that's another thing to think about the link of these two works. This is work by David Zhang, who was our intern last year. This is called ReCapture, generative video camera controls for user provided videos using masked video fine tuning. And this is a method for generating new videos with novel camera trajectories from a single user-provided video. So you can see like this is a very like ill-posed and hard problem, obviously, because you need to generate views of a video that you don't have. So you do that using some clever techniques, like basically leveraging the priors of these video diffusion models and also learning on the appearance of the video and extrapolating from there. And it actually works pretty well. We were very surprised at the results that you can get. And you can see some of the results here. So you can see the input row. So you have basically static videos on the input row. And you can add a camera motion with our method in the output row. And you can see like rotations and so for these, they're all rotations, but you'll see some zoom in, zoom outs and other things that we can do in the next slides. You can, so the idea here is that you can reimagine an existing video with a new camera motion. This encourages users to incorporate various types of camera movements into a video and making it more engaging and visually appealing with generative models. So yeah, you can imagine like camera motions are extremely important. And if you watch a movie for 10 minutes, you'll notice like the amount of variety and how much engagement it drives in you, the different camera motions, and how much emotional undertones there are with different things, like different camera motions, how much of a story camera motion can tell in some sense. So this is what we wanted, and sometimes users, can just take a video with their phone, and it's not like they're thinking about cool cinematic camera motions. And that's one thing that we wanted to achieve. Like, what happens if someone, just has a random video? Could you make it better with new generative camera motions on top of that video? So our goal is to incorporate camera movement into video without relying on 4D reconstruction, which is like a pretty big field right now, obviously. Like you can do like a NeRF or Gaussian splats, and but it takes a long time, and it's really hard with the input that we have here, with the information that we have here. Instead, we want to leverage capabilities of generative AI to do this. So yeah, I'll go really quick through this failed approach that we had, just for you to understand how hard this problem is in some sense, and then get to our successful approach. So yeah, this is the LoRa approach. Can we decouple scene motion and camera motion using LoRa fine tuning? So you maybe think of, oh, let's fine tune on a single video, and then let's fine tune on some camera motions to learn the motion, and let's try to combine both the LoRa's, right? And this is inspired by some work that we did with a student as well, called Zip LoRa a year ago now, which combined style and subject LoRa's in order to generate a subject in a different in the correct style that you wanted. So yeah, you could think of learning target video LoRa on the temporal layer and spatial layers, and then same thing with the camera motion LoRa, and then trying to combine these in an interesting way. So yeah, you can see here with a target video LoRa trained on the original video, you can actually reconstruct the video very well with the model. Obviously, this makes sense. So you can fit to the original video, and if you learn camera motion, you can try to generate a customized camera motion on top of this video by basically adding them, but you can see the subject motion is completely nullified, right? So if you do simple addition of these two and try to combine the camera motion LoRa and the target video LoRa, you get this, which, okay, it's better than nothing, but you see the kind of subject motion is completely nullified. So one idea that we explored was what happens if you have different blocks. Different blocks may control for different types of motion. So maybe you insert the camera motion LoRa's on some blocks and the target video LoRa's on some other blocks, and you combine it this way. So this is, yeah, inspired by Zip LoRa. And maybe you can have better merging procedures, and it does better. But we found that actually it wasn't worth the exploration. So you can see a little bit of like rotation of the camera here, and you can see the subject motion is preserved, but you can definitely see that this is not exactly what we want, right? So this is not as much a rotation motion as we would expect and we would want in the output video. So we worked on this for a while, and we had to abandon this direction. And instead, we came to what we think is a winning direction. One caveat here is that it does take like several minutes per video because you have test time optimization. So this is like as onerous as having like something like Dream Booth or even more, obviously. But we started with what we can achieve, like the best results we can achieve, and then trying to go from there into something that it doesn't need these test time optimizations. One thing that is really though awesome about test time optimization is that you generalize for free, right? So like obviously you take more time to process each example, but it's much easier to generalize to like a wide variety of examples. Whereas work that there's work that does, like any type of work. For example, let's just take the case of Dream Booth, right? So Dream Booth does test time optimization. If you go to other work that tries to do personalization without test time optimization, a lot of work like shows great examples, but then when you try it on something else, it fails very easily. Whereas Dream Booth has this like robustness to it, right? And I'm not saying it's the best because it takes a long time and it's very heavy, obviously, but you get this like free generalization. And I think this is the same with specifically this problem where appearance is really hard. Like video to video, there's so much appearance difference. So your prior can only be so strong, right, with the size of models that we have right now. In the future, this might be solved, but right now it's very hard to generalize to different videos. So it's just our method generalizes really well. Okay. So the method is a two-step method where first you have anchor video generation, and then you have this process called masked video fine-tuning. And I'll talk about each one separately. But let's first talk about anchor video generation. So the first idea is you generate a video of the motion that you want. So you generate kind of like a candidate video of the camera motion that you want with the subject motion that you want in the video. But with some artifacts and some problems. And it doesn't matter that it's bad. It just has to have what you want, which is the camera motion and the subject motion. It doesn't matter that it's a bit bad, and we can fix that later. And that's the lesson in this work. So here, for example, you have point cloud-based re-angling, where using a depth estimator, you can generate a point cloud of the scene, and then you can basically re-angle the scene and reproject the pixels such that you have a different angle of the scene, or in this case, like there's a translation. So the camera is moving from left to right, and you can see like this So there's a camera motion on this side. Obviously, all of these pixels are unknown. So you have like a bunch of unknown pixels that are black here. And you have some pixels that are given the subject motion, some pixels that are also unknown or uncertain here that are black. So obviously, if I give you this is really bad results, right? But trust us, we can fix this in the second stage. And that's like using our proposed technique. You can do this as well for more like bigger changes, such as rotations with multiview diffusion models. So these are basically vision models, conditioned vision models trained on different views of objects. So yeah, here, for example, Cat 3D, right? So that work is great. You should check it out. And you can generate anchor videos like this one. And you can see we have also pixels that are unknown here, and we're going to fix those artifacts. But you can generate different views of the scene. Yeah, so here you can see it, like you can see for zoom out or for translations or for Cat 3D, here you have some artifacts. And this is normal because it's a really hard problem. So these things don't fix the problem immediately, but we're going to fix these artifacts. And the idea is to have this stage 2, which is called mask video fine tuning, where you learn temporal LoRa's with a mask loss on the anchor video that we generated. So you learn temporal LoRa's on these videos that have artifacts with masks on the uncertain regions. So it would be on the regions with artifacts here or on the unknown regions here. So you want to learn the parts that are good, right? That you have the masks for the temporal LoRa. And then you want for this other LoRa that we have, the context-aware spatial LoRa, you want to learn it on the video frames, on the original video frames. So you basically learn it on the original video so that it learns the appearance of the object and subject and background. And then you combine both of these into the video model, and it works really well, basically, to regenerate the video. So once you combine the two of them, so you've generated an anchor video, you've learned from that anchor video, you have the original video, you've learned a LoRa from that original video, you combine the LoRa's, and then you do an inference pass through the video model, it can actually regenerate the scene with the motion, the camera motion, with the subject motion, and with the appearance that you want. So in this case, you see, like zoom out, you can see appearances preserved really well, and the camera motion is preserved really well. And you can see how like artifacts like these are fixed. So you can see this eye artifacts here are fixed here. You can see these missing regions are filled here and even like hallucinated. So even if you don't know what it looks like, the model will be able to hallucinate those parts based on the original frame appearances. Yeah, some ablations, if you try to, there's the anchor video, there's the just using temporal LoRa's with masks. You see some artifacts. This is using both temporal and context-aware LoRa. You still see a bit of artifacts that are finished, but this is a really good already initial result, and these are finished with SD-edit, deblurring, and de-artifacting, which I won't talk too much about today because we don't have that much time. But you can check the paper, and it's not very complicated. So here are more results. You have source videos here, and you have the ReCapture generations here. So you can see it preserves appearance really well for the scene. It does some really good 3D stuff, and also it preserves the motion of the subject. So you can see like the trunk moving here, and you can see the different angle here for that. You can see the motion of the glass here and the face, and you can see that preserved here. Same thing with this like very complicated articulated example of the car. Yeah, so we thought these were really cool results. And you can do very different camera motions. For example, you can zoom in and do rotations. So you could have some really interesting kind of camera motions like these. Yeah, so I'll leave you with some more examples for different camera transformations, and open for questions on either this part or the last part.
I have a question related to this work. So, can we control the speed and how much or by how fast we want to do the motion, and how much we want to rotate something, rotate the
Yes, Absolutely. So like the camera and trajectories are fully specified by the user. Oh yeah, that's a very important point actually, because there is work out there that is really cool right now, but only has like only supports some text-based camera movements. So you would tell it like, oh, orbit to the right, orbit to the left, or do a zoom out, etc. Right? So there's some categories, and those categories are finite. In this case, we have full control over the camera trajectory. This is also like thanks to Cat 3D, because Cat 3D has full control of the camera trajectory. So we basically inherit that capability for this work. So yeah, you could say like go fast. You could determine a trajectory that moves faster, basically, for sure.
There is a question in chat box as well.
Oh, sorry. Yeah, no, I wasn't seeing chat. Let me check it. So yeah, thank you, David. So what advice would you give to beginner, a student who is interested in this area? There's a lot of stuff that could be read. Where would be the best place to start? So yeah, I guess it really depends on whether it's like the like virtual world video game generation part, or the new like 3D re-angling part. I think there's like different literature for both. I feel like it's hard to give advice now because it goes so fast. Like everything's moving so fast. I think at the end of the day, you want to like my best advice for a beginner is get your hands into a project. So like find people that are doing cool stuff that you maybe in your institution, or maybe other institutions, but preferably in your institution because it's easier to connect. And then ask them, hey, are you doing anything cool? And also, do you need help with anything? Any way you can get into it, like, and start coding and doing things, is like the best way. And then you'll progress at the speed that you need to progress, or the speed you want to progress. But like doing things is how you get things done. And then once you want to do something, you'll go and read all about it, I think. So this is the best way to I think to do it. And this is how I did it. Like I had no research experience when I started my master's, and then that's I just started talking to professors and working on projects, and little by little you develop your taste and you find new people that do different things.
If we don't have any other question, we can conclude the session here.
Yeah, thanks everyone for coming, and yeah, feel free to shoot me a message or something.